In this lesson, we will be studying the medium-range jet transport from CAP 696. The aeroplane is based on a generic Type twin-engine jet transport, certified under CS25, large aeroplanes, Performance Class A. Compared to our previous lessons on load sheets, the load and trim sheet, which we will be dealing with later, is more complex. Our first step is to be able to understand and to extract information from the data given in CAP 696 for the medium-range twin-jet Section 4, pages 1 to 5. To start with, we will look at the balance arm location diagram and conversion table from CAP 696. During the design stage, the aeroplane is allocated a system of station numbers used as balance arms about the datum. This system also makes it possible to locate components and parts of the airframe structure. However, new variants of the original aeroplane are often made by inserting additional lengths of fuselage, and consequently, the station numbers from the original datum undergo a change. Instead of renumbering the station numbers, the manufacturer provides a conversion chart in order to determine how far a particular station is from the datum. Looking at the table converting body station to balance arm, it can be seen that this aeroplane is a variant of a previous series. Two fuselage sections, 500A to 500G, and 727A to 727G, have been inserted, which explains why the conversion chart is required. Notice that the centre section of the airframe stations, 540 to 727, are the same as the original station numbers and balance arms. Let us use the table to work two examples, converting body station to balance arm and vice versa. For the first example, we are required to convert body station 500E into a balance arm, and locating the body station 500E in the table will be our first action. Now move to the next column right, which reads 348 plus 110 inches. And finally move right to the last column to read a balance arm of 458 inches. In the second example, we are required to convert balance arm 809 inches into a station number. The first step is to locate 809 inches in the balance arm column. Now move left to the conversion column to read 727 plus 82 inches. And finally, move left to the body station column, where the 82 inches have been subtracted, to give a body station of 727D. When flying a large jet transport aeroplane, we have to be aware of a considerable change in centre of gravity, due to the extension or retraction of the flaps in flight. In CAP 696, a table is provided representing the negative moment change, when the flaps are retracted through stages from 40 degrees position to flaps up 0 position. In the table, you will see that by retracting the flaps from the 30-degree position to 0 causes a negative moment change of minus 15,000 kilogram-inches. If the flaps are extended from the 0 position to the 40-degree position, you will now have to interpret the table to show a positive moment change. In this case, it would be a positive moment change of plus 16,000 kilogram-inches. The medium-range jet transport that we are studying from CAP 696 is fitted with a stabilizer, and the pilot has to set its position in association with the flaps before takeoff. A graph is provided in CAP 696, which is used to set the stabilizer trim units against the centre of gravity for either flap 5 or flap 15 position. The setting, known as stabilizer trim units, is set to allow the elevator sufficient authority during takeoff and the first stages of flight. It will enable the pilot to rotate the aeroplane on takeoff at the correct point and maintain control during the first stages of flight. Let us work through two examples, using the stabilizer trim setting graph. The first example requires us to determine the final trim setting, given that the centre of gravity is 15% MAC, and the flaps are required to be moved from the 5-degree position to the 15-degree position. The first step is to locate the 15% MAC position on the horizontal scale, and proceed vertically to intersect the flap 5 line. Then move horizontally left and read off 4.3 units on the trim scale, which was the original setting for flap 5. Now that the flaps are required to be repositioned to the 15-degree position, we need to extend the vertical line from the 15% MAC up to intercept the flap 15-degree line. And now proceed horizontally to the trim unit line to read 3.5 units, which is the required setting for flap 15. In the second example, we are required to find the revised stabilizer trim position, as a result of a change of centre of gravity from 15% MAC to 24% MAC at the flap 5-degree position. The original plot is shown on screen, which gives a trim of 4.3 units. To solve for the change in centre of gravity to 24% MAC, we must first locate the 24% position on the centre of gravity scale. And now draw a vertical line to intercept the flap 5 line. Then proceed horizontally to the trim unit line to read 3.1 units, which is the revised setting. The cargo hold loading limitations for this aeroplane are detailed in CAP 696 by two tables, one for the forward cargo compartment, hold 1, and the other for the aft, called hold 4. In a previous lesson, we learned that the limitations are to prevent structural damage to the cargo floors. The two tables show the balance arm positions and limits, and detail the limiting running load, load intensity, and maximum compartment load. There is also a limit on the volume of cargo that can be loaded into the holds, and an overall maximum load. The centroid is the balance arm representing the centre point of that hold. To learn how to use the data in the two tables, let us work through some examples. In the first example, we are required to find the maximum compartment running load for the aft section of the forward cargo compartment. Using the table for the forward cargo compartment, locate the maximum compartment running load box in the left-hand column. And now move to the extreme right box, representing the aft section, balance arm 343 to 500, and read 13.12 kilograms per inch, which is the maximum compartment running load. In the second example, we are given a balance arm centroid of 835.5 inches for the aft cargo hold, and we are required to find out the maximum load that can be placed in that section. The first step is to locate the aft compartment centroid box in the left-hand column of the table, and move right to the next column box to read a centroid of 835.5 inches. Then move immediately up to the box above to read 3,062 kilograms, being the maximum load that can be placed in the aft cargo hold at centroid 835.5 inches. For the next example, we are asked to locate the balance arm for the forward hold centroid in the forward cargo hold, which simply requires us to locate the box showing forward hold centroid, and reading off in the adjacent box to the right 367.9 inches. In the final example, we are asked to locate the maximum total load that can be placed in the aft cargo compartment. This simply involves locating the maximum total load box in the left-hand column and moving right to read 4,187 kilograms. The medium-range jet transport fuel data page in CAP 696 details the fuel tank location and the maximum quantity of fuel allowed for each tank, both in volume and mass. There is also a table detailing the unusable fuel quantity of each tank, which is the residual fuel remaining after the tank has been drained. So that we can understand the use of the fuel tables, we will work through some examples to extract the required information, beginning with the tank location and maximum volume table. In this example, we are required to determine the maximum total volume of fuel in litres that can be loaded into the main wing tanks. The first thing is to total the maximum volume in US gallons of the left and right main tanks, which is 1,499 times 2, which equals 2,998 US gallons. We now have to convert the 2,998 US gallons to litres, and to help us to do this, we can use the conversion factor, 3.785 US gallons to litres, found in CAP 696 Section 1 under the heading Conversions. And now we can multiply the 2,998 US gallons by 3.785 to arrive at 11,347 litres, which is the total volume in the wing tanks. Part of the data in CAP 696 for the medium-range jet transport includes the length of the mean aerodynamic chord, 134.5 inches, and the distance of the mean aerodynamic chord leading edge aft of the datum, 625.6 inches. Let us remind ourselves of a previous lesson on mean aerodynamic chord by working an example using this data. In the example, we are asked to locate the position of the centre of gravity in inches from the datum, given that the centre of gravity is at 10% of the mean aerodynamic chord. Taking 10% of the mean aerodynamic chord will give us a centre of gravity position of 13.45 inches from the leading edge of the mean aerodynamic chord. We can now add this to the distance of the leading edge from the datum, 625.6 inches. This gives a centre of gravity distance from the datum of 639.05 inches. To complete the lesson on extracting data from CAP 696 for the medium-range jet transport, it is necessary to be aware of the page containing passenger and personnel data. The passenger information includes maximum load, distribution, zones and their balance arms, standard mass and baggage allowance. Allowance for crew is in a separate table. Extraction of data is simply a matter of looking in the appropriate table. In this lesson, we have covered the CAP 696 medium-range jet transport description and the aeroplane data constraints. We looked at the data for balance arm location, converting body station to balance arm, moment change due to flap retraction, stabilizer trim setting, fuel tank location, maximum volume, and the mean aerodynamic chord. Finally, we looked at the passenger and personnel data. We learnt how to use the tables to extract information which we will find necessary for future mass and balance calculations.